Um, nice. Okay. So I posted like a poll right before this meeting. I'm not sure if you guys can see it, but I want to see how many of you guys like your kind of level of knowledge in NLP/machine learning is. If you guys can like just click on a number, it's like a multiple choice poll. Or you can just type a message if you cannot see the poll. Actually, just let's just start with what year are you guys in? Year 4 chemistry. Year 4. Nice. Second year. Cool. 1A. Second. 4B. Okay. Cool. Cool. Nice. There's like a good mix of people from other years. Oh, Anthony, you're settled in. I can see you. I think this screen is although being recorded, so like you're the only face that's in the recording.
That's fine. Can you hear me, by the way? I hope it's not too white noisy. Is it okay?
I can't hear you. Is this the room like near the SLC bridge?
Yeah, that's
Okay,
the one.
cool. There's a good mix of people. Just be aware that this is like a very, very introductory workshop. And if you have done machine learning before, then this workshop might not be a lot of information to you. Not, it's just mostly just fitting a function and just some brief explanations of like some basic models used in like NLP. So yeah, now that Anthony has settled in, I guess he can get started. Or although, wait, is he lagging again?
Am I? I don't know. You tell me.
Okay, you're no longer lagging, so let's go.
Okay, great. So, shall I take it away?
Yes, take it away.
Sure. So we have the outline here. So what we're going to cover is we're going to start with the kind of lowest level of NLP, which is word embeddings, and then we're going to get into NLP models such as LSTMs, and then we're going to get into transformers, and we're going to have a code demo based on the transformers. So we can go to the next slide. And there's the giveaway at the end as well. So of course, when you're dealing with models, they don't actually understand English right off the bat. So you need to give them numbers. So word embeddings were the first kind of way to attempt to do that. So what we have here is you take a word and you give it a vector. And what's really cool about this vector is the similarity of this vector with other ones near it usually has some semantic meaning. So for example, why don't you try searching any word language? Yeah, so the nearest neighbors are dialect, programming language, spoken language, grammar. The words near language make sense in this vector space. So that is kind of the point of word embeddings. It creates a nice mapping from words into three-dimensional space. Usually they're actually in much higher dimensions, but this is usually we only see 3 dimensions, so we project it down to 3 dimensions.
Oh, this is really fun. Disney.
Disney.
Scrooge McDuck.
That's so funny. I kind of thought Goose would be higher. I'm a little
I don't
surprised.
think Goose is in there, which is weird.
Goose is. Oh, okay. It's not in there. Sure.
Oh, this is only 10K. That's barely any words.
Oh, right. Anyway, so these vectors kind of have these different dimensions, and so animals may have higher values in the yellow column there. This is kind of a way to visualize it. This may not be exactly what the vectors work out to be, But this is kind of a way to visualize why we have these higher dimensional vectors, because we have different axes to measure them on. We can measure them on if they're an animal, if they're a pet kind of animal, if they're even just maybe a food, you know, maybe they're not an animal at all. So
Here's a question in the chat.
What is the number about? So those are numbers that form a vector. So do you see, like, next to dog, there's 4 numbers. Those 4 numbers are a vector, and that represents dog in 4-dimensional space. Now, there's a way to project that down into 3 dimensions, which is what we just showed with all of those points in the cloud. And those would just have 3 columns instead of 4, of course, because it's in 3 dimensions. Does that answer your question, Tim?
So the numbers are not like as straightforward as it shows on this picture, but you can kind of think of it that way. Like each dimension, for each dimension, there's a way that the model understands of assigning like higher value to a specific dimension. So we don't know what each of the dimensions mean. No, we don't. Like there are ways to explain that, but for us, we don't know what the dimension mean. But we just need to know that the words that are similar to each other would be very, very close in like Euclidean distance.
Yeah.
The dimension. Go ahead.
Oh yeah. No, you go ahead. You go ahead. I was going to answer. I think if you mean it's 4, right? There's 4 dimensions in this picture. Is that what you meant, or?
Yeah, like in this picture, it'll be 4, but for all the models that we were talking about today, I think it will be way higher than 4 in order to encode more complex words and relationships.
So to answer your question, it's not really like the neural network coefficients. Those kind of do a different thing. These are just numbers that put together, they represent the word in vector space. That's all you really have to think about it as. And the algorithms, there are algorithms that do this. Of course, there's word2vec, there's glove. Word2vec is maximizing the probability of different words, and then glove is an unsupervised learning algorithm. And you can actually just download these vectors. So it'll give you like a dictionary. So the word dog would have its own vector, and you can download it, all of these vectors, this mapping of words to vectors. You can download them all online for free right now.
Yeah, so each of these words, you can think of it as, okay, so in the model, there's a layer called an embedding layer. It converts the word as like indices into these vectors. So what you're actually supplying to the model are just like numbers, like 1,000 or like 1,201. And then you feed it basically into a dictionary, and then it'll spit out the vector for you. And these are trained so that the input ID would map to, the word would map to the input ID, and the input ID would map to the vector. Yes, the slides will be posted in the workshop channel in the data science server.
So now that we have turned words into vectors, we can feed them into models. So there's a linear neural network. There's obviously way more models, but here are 3 kind of high-level ideas. So there's the linear neural network that someone in the chat alluded to earlier. Then there's LSTMs, which is a different type of neural network. And then there's transformers, which is yet again kind of a neural network. So we'll first start with linear neural networks. So it's basically, we're all familiar with y equals mx plus b. If you stack that up for every instance in your training set, if you have like m examples of like housing prices features, so maybe like rooms, number of rooms, bathrooms, etc., and then the output would be the value. So that would be the y in that example. That would be the price of the house. And you stack that up, each row is one house, one example, and you just do some matrix multiplication, and you end up with your prediction. And then you can train this through all sorts of mathy techniques like gradient descent and backwards propagation. So these are relatively fast, and they're pretty interpretable because you have the weights. You actually see exactly what's happening. If you put in, if you say that a house has 8 rooms, you're multiplying it by a certain weight, and you're saying, So like you're basically saying how important that is in determining the price of the house. You have an actual number. It's kind of like linear regression is used a lot in economics and all sorts of stuff because it's interpretable. Similar idea here, linear neural networks are pretty interpretable and they're easy to implement, but they don't necessarily give the best performance. So then we move on to LSTMs. This paper came out a long time ago, before all of us were born, in fact. So first of all, an LSTM is a type of recurrent neural network. So previously we saw the neural network that we're all probably familiar with. You see it on like YouTube videos and whatever. But those aren't very good for processing sequence data. So things like sentences and stuff. So we had a recurrent neural network, which is a type of neural network where it's stacked like this, and you feed in one input at a time. So if you had a sentence of 10 words, at each step you feed in one word, and then you do some math, and then you feed in the next word and you do some math, and all of this ends up producing some output. It could produce another sequence, or it could produce just one output if you're perhaps trying to guess, if you're trying to classify a sentence as a positive sentence, for example, something like that. Now, where the LSTM comes in is it produced this picture you're seeing here is a gate, and it's showing the inner workings of the gate. And what it does is, as I've described, the recurrent neural network had some problems. Basically, it would kind of forget about early words in the sentence. It would start only considering the words nearby it. This is called the vanishing gradient, for those who are interested. So basically, these gates tell it to remember which words to focus on in a sentence. So if you start a sentence with like the girl, and then you have a very long sentence, and then at the end you refer to her, these gates would kind of remind the model that like the girl refers to her at the beginning of the sentence. Alvin, if you want to add anything at any point, please feel free to, in case I'm forgetting anything.
Yeah, just to clarify, this is a LSTM cell. It's kind of like for LSTMs, it's basically just this picture, but each of these yellow circles are like a whole LSTM cell. And they still pass information from one node to another, and then you encode each word one by one in sequential order. You need to, for the next node to run, for example, for the H2 node to run, you need to have computed the node from H1 first, the output from that, feed it in, and also the second word in the sentence in order for it to produce a result for another node. And basically, the LSTM cell has like 3 gates that control the input of these information, organize them, and determine what to forget, what to remain in the cell, and pass it on to the next layer. And that's why LSTMs are way more, way better than RNNs. And I think LSTMs are usually can remember around like 100 sequences. Sequence can have a maximum sequence length of around 100. It's a massive step up from RNNs, but it's still not very good because 100 words is barely like a paragraph. And usually for text data, we're looking at something more than 100 words. And so yeah, we cannot capture long time series or sequence data. And it's slow because, as I mentioned before, in order for like the last node to run, you need to have computed the previous nodes first. And that's time consuming, and you cannot parallelize it. You have to wait for all the previous node to run, and that's not very POC. Yeah, that's LSTMs. And here comes the transformers.
But before we get onto that, we have a question. Does performance mean accuracy for linear neural network? It can. In the example that I mentioned, where if we were predicting housing prices or something, it would not mean it wouldn't mean accuracy, because you're never going to predict exactly what the housing price is. You would have a different kind of metric to say how far off you are from the housing price, rather than did you get it exactly right or not. Does that answer your question? Any other questions?
It depends on the context, but yeah, performance would usually mean like accuracy or some kind of metric depending on the model. But usually, yeah, LNNs cannot encode very complex information. And also everything that you feed into the LNN, you cannot relate to the nodes around it. So it doesn't capture locational data, while RNNs can, because you're feeding them one by one in. So you kind of know which data came first, which data came after. And yeah, moving on to transformers. There's a raccoon here because the first transformer paper came out in 2017. It's called "Attention is All You Need," and that's a very popular paper that's cited like 30 something K times, and it transformed the entire industry. So it started off as an NLP model, but it actually expanded into computer vision, um, everything. Computer vision. Fuck. Why can I not
It's now in reinforcement learning for some reason as well.
reinforcement
It's
learning?
everywhere, really.
Time series data, tabular data. It's just great at doing everything, and yeah, it's great. And basically, it's based on the idea of attention, and it's very more powerful than the LSTMs because for transformer, rather than from LSTMs, the max length is around like 100 and something, but for transformers, you're looking at every single input. You are relating with every other word in the sentence, and um, that's very powerful. And apparently, by conceptualizing these connections between words, you're able to produce a meaningful output, and that's why attention is all we need. Um, yeah, it's very versatile, and it for attention, you also do not feed in the inputs one by one. Instead, you feed in the entire sentence at the same time, and then there's like multiple heads. It's called multi-head attention that you can parallelize, and in in turn, like speeds up the inference of models of transformers. So yeah, that's what the second point is about. But yeah, all you need to get from this slide is that every word maps to every other word in the sentence in terms of how relatable each word is to each other. Now, moving on to the next slide, the attention mechanism is based on this very simple formula. It might not be very simple, but if you do not get it, it's okay. You do not need to understand it to understand the code demo. Um, just pretend to understand for like 10 more minutes, and then we'll move on to code. Um, so for every sentence that you feed into the attention mechanism, it's multiplied by weights that can be trained. And these weights, when multiplied together, produce these query and key matrices. When you multiply the query and key matrices, like when you multiply two vectors, you get kind of like a similarity matrix between those two matrices, and that's kind of where the each word mapped to each other came in, because basically for each word vector, you multiply something from the other side of from the other matrix, and it produced like basically a cosine similarity matrix with some slight adjustment, and you're able to map up the relationships between every single word in that sentence. And the value is multiplied later on to determine how important these relationships are. So one intuitive example that no, it's not called intuitive. One example that I've been telling people to try to understand it is it's kind of like a dating app. So for the guy, he could have something like long walks on the beach on his profile, and for the girl, she could have something like, "Oh, I love walking dogs" on her profile, and those two things kind of match a little bit. So those one of them is the query, the other one is the key. You multiply them together, and since they kind of match a little bit, the score will be pretty high. And for the value matrix, it basically determines how important that is. And we know that walking is not very important in a relationship. Not that I would know, but so the value would be pretty low for that specific value. And that's kind of how attention kind of works.
So we have a question. We have a question, by the way, about softmax. Akshar asks, doesn't softmax give the most likely category?
So softmax is just a function that you apply usually towards the end of a layer in order to give it like a probability. It doesn't really, it gives you a probability out of every single logit in that specific layer. Yeah, it's kind of like top product, but like QK, this is basically similarity. This is basically cosine similarity with some slight difference. You're not dividing by the other thing, you're dividing by the dimension. It's just a regularization to regularize the similarity function. Let me just enlarge this thing because I forgot to. So this is kind of like an example attention matrix. For this specific example, we're translating from English to French. I think it's French. It is French. So the first word maps to le because they are the same word. An agreement occurred stirs on the la, and then when you reach the middle, you can see that it kind of flips a little bit because European no longer associates with zone that much. Because French is reversed. European is towards the end for French, and it in turn can map to that one. And yeah, it's just basically a showcase of how the attention matrix would look like when you actually do them. And the brighter it is, the more related they are. And you might start to notice a problem here because for every word in the sentence, you have to relate to every other word, and that produces a really large memory footprint. And there's an complexity, and once you start scaling the sentences up, it gets really, really large, really, really quickly. And that also produces a limit to how much the transformers can handle in terms of maximum sequence length. But yeah, that's a problem, and you can read papers on it later. We're not going to cover how other papers have done it to resolve that problem. But due to this limitation, I think usually the maximum length is around 256 or 512. We're going to move on to BERT. This is also another paper, and I'll start talking a little bit. So if you don't understand, it's okay. The code demo would be pretty easy. BERT is basically a part of the transformer, but it optimized the transformers in a way such that it can start understanding text without having labeled data. So usually when you think of a data set, you would think of, for example, for housing prices, you would get like the, I don't know, the valuation or what the years that it has been built, and there's a label on what the actual housing price is. But BERT can start to understand like corpuses, like Wikipedia pages, without any labels. And some people cannot join. Sad. And basically, it introduces this technique called pre-training, where with corpuses of text, you do not need labels to start training. And once you have those pre-training done, you can just slap like a classifier layer, like a simple layer on top of the model, and fine tune it for different downstream tasks. And yeah, it's named after this guy because there was a previous paper called Elmo, and there's a later paper called Ernie, and there's also a pretty good paper called Big Bird. Yeah, they're just using Sesame Street characters for some reason, and it's fun, and they keep doing that. Yeah, so I talked about pre-training. The model itself, it's basically the exact same as the original transformer paper. So we don't really care. It's the encoder part, but I did not explain the encoder decoder part of the transformer. So just ignore that. There's two different pre-training techniques to understand unlabeled pages of text. The first one is called MLM. It stands for Masked Language Modeling. Basically, what happens is when you have a Wikipedia article, you have a lot of words, you mask out some of the words and you replace them with just like the mask token, which is, you can just pretend it's like a stand-in for like a word in a sentence, and you mask out 15% of the word, and the model is required to predict the actual word in that sentence. And this helps the model with learning bidirectional context. So in order to predict the middle word in a sentence, you have to know what happens before it and what happens after it, and to start making relations with the words in a sentence. And it's great. The next pre-training technique is called next sentence prediction. And a lot of models don't use this anymore, so it's very outdated. People don't care about this anymore, but I'm going to explain it. So basically, within the Wikipedia article, you take out two sentences. If they follow each other, the model's job is to say, yes, this sentence follows the other sentence. But if they don't, like if one sentence is from the top of the page and the other sentence is from the bottom of the page, then the model have to say, no, this is not, this does not follow each other. And that's how they make use of these unlabeled corpuses to start training these models. I'm just gonna skip this slide. So yeah, so as I mentioned before, once you have those pre-training done, the BERT model really easily fine-tunes into different downstream tasks. Today, the code demo is based on a classification task. So basically just a linear model, linear layer with the number of labels as the number of dimensions as output. But for these other tasks, it could be slightly different. So for the question answering task, I'm pretty sure they feed in the question and also the paragraph of words that the answer is supposed to be in. And BERT can predict like the start and end token within that paragraph. And for sentence tagging tasks, it's you basically feed in a sentence and then you fine tune the model so that it can predict like the part of speech, like is this word a noun or is this word an adjective, and so on. I think it's now, yep, it's now code demo. Anthony, take it away.
Okay. Yeah, sure, I'll take it away. So can I share my screen? I hope I can.
I really hope you can.
I really hope I can. Hello. So are you guys seeing this? Can I don't think I can see the chat while I'm like doing this.
I can. I'll just start reading the chat.
Yeah, okay, great. So we're good. Everyone can see what I'm seeing. We're on UW Flow. You may be familiar with this website. I'm not sure, maybe not. But is it the case that you guys are familiar with this? Yeah. No? Okay. Anyways, it's a website that has a bunch of reviews about courses. That's all you guys got to know. All right, sweet. So what are we doing with this? So the goal today is to build a model that will take in a review from a student and predict whether or not they liked the course or not. Now, let's take CS 115, for example. So things like go to office hours and practice. You know, it's hard to tell if that person liked the course, but they did give it a thumbs up. So that's kind of, just so you guys are on the same page, this is basically the ground truth that we use to train the model. We used a thumbs up or thumbs down that they gave. So one of my least favorite courses, although things are nicely organized, Racket's such an annoying language, and that is true. That is a true fact right there. Racket is annoying. They gave it a thumbs down. But you might be asking, like, what's the point of building this model? Well, what if one day UW Flow got rid of these thumbs up? Could be useful to kind of quickly go through 86 reviews and say, hey, like most people did or didn't like this course. You know, it could be useful like that, but also there's some times where people don't give any ratings at all. So never taken anything remotely related, and this was super easy. So they probably liked the course, this person, but it would be nice because there's literally thousands of reviews. It'd be nice to do this all in a systematic way. So there's no rating here, so that would be fun to find out. So we're going to go through the code of the actual training. I believe I'll just go through Colab. This should be made publicly available, but if not, it's on a GitHub that is publicly available as we speak, actually.
I'll send the GitHub links.
Yeah, sure.
Or actually, I'll share the collab link right now to.
Okay, cool. One of them might not be public yet, so I'll have to do that after. But you can share the link anyways, and it'll become public shortly after the meeting is over. So anyways, we'll go through the code. So here's, we're using TensorFlow, which is a deep learning framework developed by Google, one of the most popular ones. And it's honestly, like, if you guys are looking to learn a deep learning framework to put on your resume, I definitely recommend, I would definitely say TensorFlow is probably the easier one. There's PyTorch also, which is pretty popular. It's actually gaining in popularity right now, but TensorFlow is pretty easy. They have the Keras library, which is really nice. So anyways, so this is just importing libraries, nothing special, and we're reading in the data. This is the data that I web scraped. The code to web scrape UW flow is also publicly available, but you know, if all of you use it all at once, you'd probably crash the website, so don't do that. But here's how the data looks. So it's basically what you see online. Like at the course level, you see all of this, it's the same, but each row is a different review. So go to office hours and practice, that was the first one we saw. One of my least favorite courses, I also pointed that one out. They disliked the course, and I gave that a 0. So if they disliked the course, I encoded that as a 0. Alvin, if I have any questions, feel free to let me know and interrupt me, because I don't want to go too far past if there's any questions. So here's the first review, just to see what it looks like. In Python, it's just a string, right? Nothing crazy there. So the only things we really need are course code, review, text, and label to train the model. We don't even really need course code, but in case we wanted to go back and assign the reviews back to what course they came from, that'd be nice. But anyways, so we also had those situations where there's no rating. We can't really train the model on that. Like you could, but we're just gonna get rid of them for the purposes of this code demo. So we then are pre-processing the label, which is the 1 or 0. Instead of leaving it as a 1 or 0, we chose to one-hot encode them. And what that means is there should be a picture, but it's not actually coming, which is kind of unfortunate. Yeah, I guess it's just not working. But basically, one-hot encoding means instead of having 0s or 1s, it'll be 2 columns, and one of the columns is for all the 0s, and one of the columns is all for the 1s. So this one is a 1, so it would, in the column for 1s, it would have a 1 in that spot. This would be a lot clearer if I had the picture, but I don't, so we're gonna move on. So once we make these one-hot vectors, then we just split up the test set, or the data set into a training and test set. The test set's important. You have to set aside your test set all the time at the beginning to make sure you don't accidentally train the model on things that it's going to get tested on, because then you'll get artificially inflated metrics. Now here's the TensorFlow specific stuff. So we have TensorFlow add-ons and just the library TensorFlow, as well as transformers from Hugging Face, Hugging Face is a company that has a website that hosts a bunch of models. They have all sorts of stuff there. We'll actually cover that briefly. This is the finished product. So this is Hugging Face's website. Finished product, you can type in course review, blah, 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 and you can ask it to compute it, but we'll leave that for a little bit after. And if I'm going too fast, you guys can tell me to. I apologize if I am. So we're downloading the Dilbert tokenizer, which is the part where in the slideshow you guys saw how each word was represented by a number. That's what the tokenizer does. So we download the pre-trained tokenizer for Dilbert, and we tokenize the examples. So we make the training data set and the test data set from the tokenized data. And here's what the tokenized data looks like. So 101 is the start of the string, and then all of these tokens represent different words. And then down here is the attention mask. So when we had that softmax formula on the screen, this is like the matrix that ends up coming out. So we have 1s in places where we want to pay attention to, and 0s in places where we're not paying attention to. So we need to set our hyperparameters. So for training, you need to specify the max length. This has a big impact on how long it takes to train, and so it's pretty important. As well as epochs and batch size. Epochs just means how many times we're going to go through the whole data set, And what are the sizes of the batches? The reason we use batches is because it makes it a lot faster to compute gradients. So all you really need to know is it makes it faster. So there's a learning rate as well that is the scalar that we multiply the gradients by to kind of slow down or speed up how fast we're learning. And then there's the number of training steps, weight, decay rate, don't worry about that. Yeah, so then we download, this is literally just downloading the model from this website. That's all it's doing. And then we're specifying the metric. Don't ignore this, I don't know why it's there. So we're just specifying the metrics from TensorFlow. We're using something called F1 score. Anyone familiar with classifications probably familiar with it, but basically it's just a score to say how accurate we're being. We're not using accuracy because usually people don't use accuracy. F1 score is obviously sometimes more common depending on the task. So lastly, this is how a TensorFlow model compiles. You specify what optimizer. So this is just a math function, basically. You just specify that. Also, loss is also a math function, and we're using categorical cross entropy. Don't really need to worry about that, but it's probably the most common loss function for a classification task. And then you specify the metric that we created right here. The F1 score is the metric. And then you call model fit with the training, epochs, and validation data set. And you save the model. Now, we're actually going to use it. This is something called Gradio. Oh, what's up?
I have a few questions, not from the
Sure.
chat, but why?
Oh, there's the
what's
pick.
the Stillbird?
Nice. What's the
Stillbird?
It's your favorite model, Alvin. You feel free to hop in.
Oh, okay. All right. I have slides for that, but do I really want it? It's like exactly one slide. Okay, so basically, actually minimize my space. I don't want to see my face.
Okay, sorry.
So basically, we have the BERT model. It works great, and it's great, but what's not great is that it's too big, and usually people want to run these models not on like a very big device. They want to run it on their phones, or they want to run on edge devices. So Distillbird basically allows you. It's basically like a slimmed down version of BERT, and it's like I think 60% faster than the normal BERT model, and retains like 90-something% of the performance within the bigger BERT model, and it's great. And they did it by a thing called distillation. And what distillation is you can think of it as a teacher-student situation. So the teacher in this situation would be the larger BERT model. It takes a long time to load, to inference, and to train. But it knows stuff. It has knowledge, and it's gonna teach it to the student, which is the smaller model, which is the Stillbird, which works way faster, but still has a good amount of knowledge. And basically, the Stillbird is trained on the logits that the BERT model predicted for a specific task. And you might be wondering, why can't I just train this smaller Distillbird model on a labeled data set where I can just train it on IMDb reviews? I can train it on like a specific, very concrete label. Why do I train it on this BERT model who might not be as accurate? Well, that's because of something called dark knowledge. And it sounds weird, but basically, not every class is distinct from each other, like all the time. So, for example, if you're classifying between 3 different animals, like frog, cat, and dog, cat and frog are very different, but cat and dog are kind of the same, and you should allow it some leeway when the model predicted a cat as a dog, because you can understand why that happened. But if you predicted a cat as a frog, then that's basically no, and that's not good. And BERT model, when you predict these things, they have a score from the softmax layer. You know the probability of a specific object being a cat, and these are not solid labels. They're like 0.8 or 0.6 percent chance of being a cat, and you can use these dark knowledge to train a model way better than just using a discrete label. That's my spiel. Second question, Anthony. Let's say someone wants to fine tune it for like 4 classes. How should they change the code to adapt to that?
Oh, that's a good question. So do you remember when I said, I'll actually maybe run it. Do you remember when I said that we made one hot vectors? I'll show you exactly what I meant by that. You know what? Colab is some stuff. You know what? I'll just quickly hop into my real notebook. Colab is sometimes weird. Also, it's not letting me.
Wait, should I do it?
I should be able to do it. Should be
Okay,
fine.
cool.
Okay. Sorry about that, guys. So here's the data, and there's the picture, by the way. It's about to come up. All right. So bam. So we said we make one hot vectors, right? So we have one hot. This is what they actually look like, and I'll show you what I meant by one hot. Now I can show you. So this is like the column for zeros. So anything, if any row has a 1 in this column, that means that that review did not like the course. This one means that they did like the course. So that's what we mean. So when we would add more labels, we would just simply add more columns to this. So you would have, like, if you wanted to have 4, you said you would have 4 columns, and you would only have a 1 in each of the 4 columns for each row. Does that make sense? So you would do something like, hello?
Yep. I
Sorry,
think there's 2 more places.
Okay. Sorry?
There's 2 more places
2 more places? What do you mean?
to change the number of classes.
Oh, yeah. Oh, like it literally changed everything? Well, I don't know.
Oh, not to change it right now, but like if they want to initialize the model or train it.
I wanted to train.
Wait.
Oh, where else would you change the code? Like what other spots you're saying?
Yes.
Oh, right. Okay, fair enough. So you'd also have to specify the number. So there's some classes that we call number of classes. So instead of 2, you change that to 4. But more importantly, this one, number of labels. So when you're specifically downloading Distilbert based on case, you would change number of labels to 4 as well there. So I think that pretty much covers it, right?
Yeah, I think that's it too.
Okay. Is there any other questions?
No.
Okay. Super cool. I'm going to briefly go over Hugging Face Trainer, which is another way to do it. And it's pretty, like if you're not familiar with TensorFlow or PyTorch or anything, it's pretty nice. I'll just quickly go over it. Not going to be as in-depth as TensorFlow. That wasn't even particularly in-depth, but generally, so the first thing worth mentioning is it does use PyTorch, but you don't have to really understand that much about PyTorch to make it work. You build your data set from, like, in a similar way to how we built a data set with TensorFlow. You build it with, like, the label and the text, yeah. You specify the model name. Once again, you download the tokenizer, same thing. And you tokenize each text. So that's what's going on here. We're literally just each review, we're tokenizing it and we're mapping it onto the whole data set. And one of the main differences is that when you download the model from Hugging Face, you have to specify the ID to label. So ID would be 0, and that means bad course. ID would mean 1, that means good course. And then similarly, it's like the backwards mapping. So you provide that to auto model for sequence classification. And then once again, we use F1 score, so you have this function. And then then this is the other main difference. For Hugging Face Trainer, you have to pass a training arguments object. So you create that with where you want to save it, number of training epochs, a lot of the same stuff that we did with TensorFlow. So for example, we have the same batch size, I think the same weight decay, same learning rate, number of epochs, same thing. And then you can actually push directly to the hub from with this training argument. You would say true, and then that's how you would get something like this, which is, this is our model on Hugging Face. It's being posted over there. and we kind of named it Unibuster 9000 Ultimate Course Review Classifier. And that name was provided to us by GPT-3, which is another transformer. So yes, the AI is naming itself nowadays. That's basically what happened there. So we create our trainer by passing it the training arguments, give it the model name, the metrics, the data, and the tokenizer, and then you can call it trainer.train, and that's pretty much it. So it's pretty friendly to, if you don't really know what's going on under the hood, it's pretty friendly. Hugging Face's whole mission is to democratize machine learning, and that involves giving access to state-of-the-art models to people who may not know everything about the state-of-the-art models. So that's what Hugging Face is doing. Now, earlier I mentioned this review. We don't know if they liked it. Let's find out if our model that we trained on all these reviews thinks that this person liked it. If you're gonna ask me, I think it should be positive because it sounds like super easy. It sounds like they had a good time.
It would be
So
really
Hugging Face
embarrassing
actually posted it.
not.
Yeah, it'd be embarrassing if we're wrong. So I haven't tested this, but yeah. So hosted inference means that Hugging Face is using its own servers to answer questions with our model that we gave it. So you can play around with other ones too. There's things like generative AI. You can have it on Hugging Face. You can actually go and generate your own AI images and stuff like that. So let's see. Model loading. Model could not be loaded. If it doesn't work, I'll be sad. There it is. Good course. It's not that sure about it though, but it's 86%. I mean, hey, look at that. So our model does a thing. It predicted that this reviewer thought the course was good. So that's pretty nice. Now, lastly, this is Gradio, and this is where we're actually going to look at the course as a whole, right? So we're going to actually take a course such as AXI 232 for no particular reason other than there's not that many reviews. It can take a while to run, to have the model predict its outputs. It can take a while, but there's 8 reviews here. They're all positive. So it should say 8 good courses. So that's what we're going to do. So basically, there's a drop down that I made with all of the courses, and each course, like when you click one, it'll look at all the reviews for that course, and it'll give you the counts of how many times it said good course versus bad course. 2. And see what happens. Aha, it figured out that all 8 of those reviews were good reviews. It thinks that there's 8 people who said it was a good course, and lo and behold, that is the case. There are 8 likes on these reviews. So that's our Gradio demo. I hope that you learned a thing or two. I will now be taking questions. I shouldn't have closed that. I'll now be taking questions. And if you guys have any courses you particularly hate or want to see what our model thinks about them, I can actually search them up right now. So please, if you guys don't have any questions, someone give me a course in the chat and I'll search it up and we'll have a good time like that. So like PD1. PD1 is surprising, actually. A lot of the reviews are like kind of positive about it. I've already tested this one out. It won't be as like hated as Reddit would have you believe. But yeah, so what's up in the chat? Oh no, actually 112 bad courses. Okay, I guess I misunderstood it last time. Yeah, that makes sense. There's 112 bad courses and 15 good courses. Yeah, that's because everyone hates PD. Anyone who's done PD, show your hands. Represent in chat. Okay, we got all PD courses. I'll just stick to the one, but I'll go to AFM 101 next. That's so funny. This is actually pretty fast. It was going a lot slower before. Pretty happy. So for AFM, it's like a mixed bag. Like 56 good course, mostly good. 28 people said it was bad. We'll try MSC. This one might not have any reviews because it's a 600 course. So I really doubt that there is like any reviews in the first place. But let's see. Yeah, it's not even there. There's 603 though. We'll do 603, but I don't think there's any reviews. Oh, there's just one review and it's good. Yeah, it's hard. Phys 121. I took that course and I did not do well. That's because I was in first year mode though. Wasn't ready for the physics of Waterloo.
The model is Only capable for text, yes, text classification for the fine-tuned model, yes. But when you download it as like the Stobert base uncased, you can fine-tune it for different stuff like mass language modeling. But I don't like mass language modeling is not like a real fine-tuned task. People don't usually do that.
Let's try math 145 was the last one I saw in chat. Let's see, physics was mostly positive. I think most of the reviews are positive, so that's one of the things. Wow, actually, people really like math 145. I guess that speaks, I feel like the teachers in math 145 are really good usually. People usually have good things to say about the teachers. But yeah,
Just send a link in the chat. It's basically the hosted model of this classifier if you want to test it out. And you can do the same for your own models. It's pretty easy to publish to the Hugging Face Hub and host it for other people to like inference with. And this is especially helpful if you want to demo it to your recruiters or people who don't know machine learning but wants to run your models and stuff.
Exactly.
Yeah, Hugging Face Hub is great. It's my second favorite hub.
What's your first favorite?
GitHub.
GitHub. That's fair. That's a good point. By the way, most people like CS135. I call cap on that. I think the models are wrong on this one, or all the reviews are not representative. Because I heard most people usually hate CS135. I took it too, and I thought it was fine.
Ali. So there's a question from Ali. Shouldn't there be a third class? Well, the model is trained on 2 classes, and so it can only predict 2 classes. But let me see if I have anything open. Shit, I do not.
Oh, I can. If there's no more courses, I'll stop sharing my screen and you can take over again.
But yeah, one way if you want to do like an OK class after training, you can just look at the logits and then it doesn't reach a specific threshold that you want. For example, 0.7, you can just classify it as OK because not even the classifier can determine whether it's like very, very good or very, very bad. It's kind of in like the middle, and you can classify that as so there's a giveaway, and it's just stickers. It's like laptop stickers with geese on it. It's wacky. I thought I would do that just so people would actually run the code. So if you want to participate in the giveaway, it's a good time to pull up your Colab notebooks. The one I sent, you can use that. And yeah, basically the stickers look like that. They're kind of cute. They're still being delivered, so you can redeem them like October or something. But yeah, there's like at least 3 with keys, and at least one of them is a meme. Actually, 2 of them are memes. Three of them are memes. So yeah, and basically, sorry, I'm reading the chat. So do the numbers mean anything? No, it's just a direct mapping to the text labels.
Yeah, we made that up basically.
You only need that for the TF trainer, but you don't need that for the TensorFlow one. And usually, if your labels don't have specific like scale, then it doesn't matter. Like 0, 1, 2, it doesn't matter. But if you're doing like Likert scale, where it's like I somewhat like it, I like it, then maybe you would want to do it in order, just so it's easier. I would also send the prompt in the chat. I'm gonna gauge how many people participate in this giveaway and then see whether I would do the next one. Yeah, so pull up your Colab notebooks. The fastest 2 would get like 3 stickers. The person would send the answer, and obviously people would copy the answer. So the second person, you have to send the screenshot of the code that you used to create that answer. So yeah, So basically, if you look into our server, you're peeking into the DMs between me and Anthony. So if you look at the server, and if you look at the poster for this specific workshop, you would see that the person is saying something and the goose is also saying something. The task is to translate that to English words and then put that in the workshops channel. So the workshops channel is here. And I guess the fastest person get like a prize of stickers if you guys are into that. So yeah, that's it. I'm gonna continue receiving questions if you guys have any. And yeah, I'm gonna end this workshop.
Aw, you're welcome. Thank you to Alvin and his 3 GPUs that made this model possible.
Thank you to Victor, who somewhat contributed to the 3 GPUs.
Yeah, thank you to everyone who contributed. That made it a lot more enjoyable. If I was just speaking with no questions at all, and if Alvin were speaking with no questions at all. All right.